This video is going to take us through some more chain rule problems. So we're going to look at how to combine it with other rules and how to use tables and graphs in doing this. So just a refresher on what the chain rule is. It's used to differentiate a composite function. That is when you have a function, in this case g of x, inside of another function that we are calling f. And here's the chain rule. So we do derivative of the outside, so that's f prime. We leave the inside function alone, so g of x we just write exactly as is, and then we multiply times the derivative of that inner function. This first example will show us how to use a chain rule in conjunction with a product rule. So chain and product. So when I look at this, I see x squared times this binomial to the fourth power, and it is that multiplication symbol right there that makes me know I need to use a product rule. So I've got x squared as my first function and 3x plus 4 to the fourth as my second function. I'm just going to run through the product rule. So it's going to be first function, that's the x squared, times derivative of the second. Notice when I wrote that I didn't actually do the derivative. Sometimes you get lost inside of doing this derivative, which is going to involve a chain rule, that you forget to do the second half of the product rule. So I'm just going to keep the flow of my product rule going. So I have first times derivative of the second plus the second function times derivative of the first. And I can do that x squared derivative pretty quickly and just call that 2x. So it's not mandatory that you write this notation. You can just do that derivative on the fly once you get comfortable with doing the chain rule. But this just splits it up into two steps. So my first step is focusing on the product rule, and now my next step is going to focus on the chain rule. So now my focus is going to be just on doing this derivative right here. And what I see is that 3x plus 1 is my inside function, and that fourth power is my outside function. So I'm going to start by doing the derivative of the outside. So that was just a power rule. So bring down the power and subtract 1 from the power. Leave the inside alone. And then multiply times the derivative of that inside function, which would just be a 3. And the rest of this has already been done. So pretty much that's all the calculus involved. The rest of this is going to be simplifying our answer here. And what I'm going to do first is take this 4 and this 3 and multiply them together. Now when I look at this, I've got two terms sitting right here. So this is my first term, and this plus separates that from my second term, and my second term is this one. And what I'm going to do is factor. And to do that, I look for factors that my two terms have in common. I'm going to start with the coefficients. So I have a 12 and a 2, and I know I can factor a 2 out of that. Out of my x squared and my x, I know I can factor an x out of those two. And my two terms also have this 3x plus 1 factor in common. This one is to the third power, this one's to the fourth power, but I can factor out a 3x plus 1 to that lower power. So I'm going to factor out a 3x plus 1 cubed. So this is what I'm going to factor out of each of these two terms, and in the parentheses I'm going to write what's left out of each one of them. When you factor, you can just imagine it as a division problem. So just imagine dividing this 2x, 3x plus 1 cubed out of that first term and just write what's left in the parentheses. So 12 divided by the 2 is going to be a 6. X squared divided by x is going to leave an x. And all three of these 3x plus 1s have been factored to the outside of the parentheses, so this is all that's left. I'm now to this plus sign, so I have plus, and now I'm going to factor my common factor out of my second term. So the 2x divided by 2x is going to leave nothing there. I've got 4 3x plus 1s, and I'm factoring 3 of them out. So that's going to leave me a 3x plus 1 inside the parentheses. And now all that's left for me to do is combine my like terms in the parentheses. And this is my final answer. Our next example is going to look at how you use a chain with a quotient rule. And on this one, I see that I have a quotient in here, and that quotient is being raised to the fifth power. So this quotient is my inside function, and the fifth power is my outside function. So I'm actually going to start this with a chain, and in doing the chain, I'm going to run into the quotient. So I start by doing the derivative of the outside. So the outer function is that fifth power. So it's 5, and I'm going to subtract 1 from the power. I leave the inside alone, so I'm just going to rewrite that inner function as is. And then I multiply times the derivative of that inner function. And similar to what I did before, I just wrote that I'm going to do the derivative without actually doing it, so I could finish my chain rule flow of thought before I start thinking about that quotient rule. So now my focus is just going to be on doing this derivative, which is going to be my quotient rule. And so here's my quotient rule, and pretty much this is my derivative. The rest of this is just going to be simplifying. So in this numerator, just getting rid of those times 1s, they're not really doing anything. And then I can see my x minus x is just going to zero out. And in my next step, I'm going to take that fourth power, and I'm going to give it to the numerator and to the denominator, so I'm sitting here. And then what I see here is that down here I have that common binomial, so if I have the same base, I can actually add these exponents. So my final answer is, so I've got 5x to the fourth in my numerator, and then down here multiplying these two with that common base gives me x plus 1 to the sixth power. And that is my final answer. Next we'll look at a problem where we have multiple iterations of that chain rule. So we've got 3 or more functions. So the first thing I would say on this one is relocate that power right here and just write it on the outside. And when you do that, you can see that you have a function that's inside of another function that is inside of another function. So there's 3 layers going on to this one. So I'm going to define the inner, the middle, and then the outer functions. So since I have an extra layer, instead of just having the y and the u, I'm going to have a new letter that I'm going to call v to represent that innermost function. So that inside function is that 10x minus 3, and I'm going to define that as v. And you can see we are doing the cosine of that v. So my next function is going to be cosine of v is going to represent this one. And then this whole amount, this cosine v, is being raised to the fourth power. So that is my y. So y is going to be u to the fourth power. So my 10x minus 3 is inside the cosine, which is inside of that fourth power function. So they're all nested within one another. And the next thing I'm going to do is find the derivative of each one of these with respect to the variables that appear within them. So here's all my derivatives. Derivative of v with respect to its variable x is just a 10. Derivative of u with respect to its variable v is negative sine of v. And y equals u to the fourth, so dy du, my variable, is just 4u cubed. And look what happens when I multiply all of these together. So you can see when I write it like this and I multiply all of these derivatives together, I can see that my dv cancels with dv, my du on top cancels with that du on the bottom, and what I'm left with is dy dx, and that is precisely what I'm trying to find. In other words, all I really need to do is take all of these derivatives and multiply them together. And that brings me here, and I just went ahead and multiplied the 10, the negative, and the 4 together. That's where the negative 40 comes from. And then my u cubed and my sine of v. And what we said in the previous video was if we want dy dx, if this is a variable x, we do not want these u's and v's running around in our answer, but I have my defined values for u and v over here. So what I need to do now is just back substitute. So where I see the u, I'm going to put in a cosine v, and where I see the v, I'm going to put in a 10x minus 3. So in for my u, I put the cosine v, in for my v, I put the 10x minus 3, and now I just have one more step to go, because if I want this in terms of x, I still have a v sitting here. So my last step was to replace that v with the 10x minus 3, and now I have everything in terms of x, and this is my derivative. Let's take a look at some table questions here. So I first have a function h that's defined as f of g of x, and I see that's a composite function. If I want to find h prime of 2, I first have to find h prime of x using the chain rule. And then every place I see an x, I'm going to replace it with a 2. So all of these x's will now be 2's because that's what I'm going to evaluate this function at. And now I'm ready to look at my table, and I see that g of 2 is what I need to look up first. So g of 2 is 1, and g prime of 2 is a 4. Now just be careful in this next step because this says f prime of 1, not f prime times 1. So I have to look up f prime evaluated at 1. So f prime of 1 is that negative 3. And negative 3 times 4 is negative 12, and that is my final answer. This next question defines a function called m as f of 2x. And what I see when I look at this is that 2x is a function inside of my function f. So that 2x is my inside function and f is my outside function. So to find the derivative, I need to use the chain rule. So my chain rule looks like this. So derivative of that outside function is f prime. Leave the inside function alone is the 2x times derivative of that inside function, and derivative of 2x is this 2. And now if I want to evaluate this derivative at x equals 2, I just replace the x's with a 2. And now I look up f prime of 4. So f prime of 4 is negative 6. And negative 6 times 2 is negative 12. And that is my final answer. Just coincidence that I got the negative 12 for both of these. And our last question type, we'll look at how you do this when you're given a graph of some functions. So again, when I look at this, I see that p of x is my function, and it's defined as a composite function. So h of x is my inside function, and j is my outside function. So before I even start thinking about what I'm going to do with this 1, I'm going to find p prime of x. Here is derivative of the outside function, j prime. Leave the inside function alone, that's my h of x, times derivative of the inside function. And now I'm ready to evaluate this at an x value of 1. So I'm going to start by doing h of 1. So I look over my graph. H is the solid line here. So h of 1 looks like it's got a value of 3. Now when I go to evaluate h prime of 1, and all I have is a graph of h, just remember that a derivative just means a slope. So what this really wants is just the slope of h at 1. So I'm looking at this linear piece of the graph right here. And I can see from this point, I go down 3 and over 1. So my slope here at 1, at x equals 1, is a negative 3. And I use that same thought process when I do j prime of 3. If all I have is a graph of j prime, it means the slope. Derivative is a slope. So the slope at 3. So I'm looking right here because 3 is my point right here. So I want to know what the slope is of this linear piece right here. So I just count it out. So it looks like I go down 1 and over 1, 2, 3. So my slope is going to be negative 1/3. And when I multiply these two together, I get my p prime of 1 is just going to be, looks like 1. And that is my final answer.